Chapter 2 of The Good Earth. There are 6 different categories we will be discussing: old ideas and new ideas, the origin of the universe, stars and planets, our solar system, Earth, Sun, and the seasons, and why we have temperature variation, and the unique composition of planet Earth. Old and new ideas. Why is the Earth the only planet known to support life? How have our views of Earth's position in space changed over time? And why is it warmer in the summer and colder in the winter? Or how does Earth's position relative to the sun control the climate? A long time ago, people believed that we had a geocentric system. They believed everything revolved around the Earth. And there was a switch from this geocentric, or Earth at the center of the universe, to a heliocentric system. Geocentric orbit hypothesis. Ancient civilizations interpreted rising of the sun in the east and setting in the west to indicate that the sun and other planets revolved around the Earth. In other words, Earth was the center of their universe. This idea remained the dominant idea for more than 2,000 years. Heliocentric orbit was an idea in the 16th century, and it was confirmed by Galileo in the early 17th century with the phases of Venus. If you look at the changes in the size and shape of Venus as observed from Earth, you can see it in this diagram. This is what led Galileo to say that he had proof. Galileo used the early telescopes to observe the changes in the size and shape of Venus as it revolved around the sun. Origin of the universe. We have Earth, and it's a small rocky planet, third from the sun, and it orbits the sun, which is a medium-sized star, and it's one of the billions of stars that are in our galaxy, the Milky Way. It's one of the billions of galaxies in the universe. But how can we tell what the size of the universe is? We use luminosity, which is the brightness of the pulsating stars. This was used to determine the distance from Earth, so the brighter stars are closer to Earth, and the dimmer stars are farther away. And these measurements have been repeated to determine the variables. They're moving away from Earth. The interpretation of this is the universe is expanding. One of the examples in the textbook, a police car with a pitching siren. The Doppler effect, the apparent change of the frequency of sound waves or light waves due to the motion of the source relative to an observer. For example, the change in the frequency or the pitch of a siren from a passing police car. Further explanation: no change in frequency for sound waves when the police siren and the observer are stationary. In other words, the person is just standing and the car is not moving. The siren is going off, but there's no change in the sound of the siren. is called normal frequency. Higher frequency when sound waves are compressed for objects moving toward an observer. Observer hears the higher frequency or the shorter wavelength siren for an approaching police car. The lower frequency occurs when the sound waves are stretched out for when objects are moving away from the observer. The lower frequency or the longer wavelength siren is heard for a police car moving away from the observer. This is the Doppler effect. The apparent change in the frequency of sound waves or light waves due to the motion of a source relative to the observer. Sound and light waves are compressed or closer together for objects moving toward an observer. Sound and light waves are stretched out for objects moving away from an observer. The change in frequency of a passing siren can be used to determine the speed of the police car. Light on Earth is a form of solar radiation, and it occurs at specific wavelengths from 380 to 250 nanometers. Hang in there, this will make sense in just a second. The wavelength of the visible light is shorter. It moves from shorter wavelength to the longer wavelength. The color of the light from distant stars, it's stretched toward wavelengths at the red end of the spectrum, just like the sound waves of a police car moving away. Astronomers use the degree of redshift, and that's what this effect is called, to determine the distance to faraway galaxies, more than 13 billion light years from Earth. The size and age of the universe. If the color of light from other stars is shifted toward the red end of the spectrum, then other objects in the universe are moving away from Earth and from each other. If they're going the other direction, it will be a different color. The farther away the star, the greater the redshift and the faster the star is moving away from us. Therefore, the universe must be expanding. Light from the most distant star has traveled more than 13 billion light years in 13 billion years. This feeds into the Big Bang theory. The expansion of the universe suggests the universe began with an episode of rapid expansion from a much more compact form. The almost instantaneous period of rapid expansion is known as the Big Bang. Within hours of the Big Bang, simple elements, hydrogen and helium, formed as a subatomic particles combined. Hydrogen is 1 proton plus 1 electron. Helium is 2 protons and 2 neutrons and 2 electrons. Just those 3 elements, hydrogen, oxygen, carbon, make up 90% of the human body. 5 more, nitrogen, calcium, phosphorus, potassium, sulfur, make up just 9% more. Small amounts of many other elements are needed for life. Hydrogen was formed soon after the Big Bang. Other elements and complex compounds formed during the life cycle of stars. Gravity pulled together irregular clouds of gas and dust, which was generated from the Big Bang to form galaxies, which are systems of stars. You ever seen the Milky Way? Stars and galaxies in a small section of the universe. This is an image taken by the Hubble Space Telescope. I actually saw the Hubble Space Telescope launched from Florida, from Cape Canaveral, on one of the space shuttles. This is a false color image from the NASA Spitzer Space Telescope. It's a false color because they added the color to it. It shows cool gas and dust that are the incubators for a new star. Gas and dust material clumped together to form millions of stars, which is an ongoing process. Very high temperatures and pressures in the interiors of stars fuses hydrogen atoms together. Nuclear fusion. This forms helium. When the stars burn out, the hydrogen has been used up. Life cycle and types of stars. Stars vary in age and size. There are giant stars that are 100 to 1,000 times brighter than the sun, but they burn out faster than the sun does. Giant stars burn out in 10 to 20 million years. Intermediate-sized stars, such as the sun, will last approximately 10 billion years. The sun will collapse when the hydrogen is used up, just like any other star. This will result in a temporary temperature rise and expansion to form a red giant star. Higher temperatures would fuel more fusion, converting helium to carbon. The fusion would end when helium is used up. The loss of the heat of the fusion would form a smaller white dwarf star that will cool to a black dwarf star. Kepler's supernova. An astronomer named Kepler noted the appearance of a new star, which is the supernova, on October 9th, 1604. Giant stars collapse over multiple stages, initially forming red supergiant stars. The collapse forms increasingly complex elements. For example, carbon changes to oxygen. The final stage is a massive explosion, the supernova, that fuses together heavier elements and blasts them through the universe. When stars form, they're surrounded by a rotating disk of cosmic debris. Gravity pulls debris together to form planets that revolve in a consistent direction around a star. The heavier, rocky planets are closer to the star. The lighter, gas-rich planets are farther from the star. Potentially thousands or millions of extrasolar planets revolve around other stars. Our solar system. Here is a photograph of the sun. Another photograph of the sun showing a solar flare. Notice the approximate size of the Earth, that little spot at the bottom. The solar system, sun and surrounding planets. The sun is 99.8% of the total mass of the entire solar system. The sun is 150 kilometers from Earth, and it undergoes a differential rotation, which means that the equatorial region rotates faster than the polar regions. Wow. And you might say to yourself, well, how does that happen? It's all together on one sphere. Think about it. The sun is made of gas. Therefore, the equatorial region can move separate from the polar region. This results in disruptions of sun's magnetic field, and it produces sunspots and solar flares. Sunspot cycle is a variation in the number of sunspots over an 11-year cycle. There are few sunspots visible during the solar minimum and more than 100 sunspots during the solar maximum. The solar wind is a stream of charged particles emitted from the sun's magnetic field, and the solar wind affects a volume of space known as the heliosphere. The interactions of the solar wind with Earth's magnetic field creates the aurora borealis, which is in the upper atmosphere of the polar regions. Occasional solar eruptions can disrupt Earth's magnetic field to produce electrical blackouts. Satellites are in greater danger from solar flares than features on the surface are. They're closer, and there's no atmosphere to protect them. Also, in this particular image are the principal gases that are present on each one. If you look at this, you can see that on Earth we have mostly nitrogen. Now you would think that our atmosphere is made up of mostly oxygen, but it's really not. Our atmosphere, the air that we breathe, has only 21% oxygen. Mars has mostly carbon dioxide. Jupiter, Saturn, Uranus, and Neptune have hydrogen and helium. Those are the lighter gas planets, and they are farther from the sun. We have 8 planets and 4 terrestrial planets. We have Mercury, Venus, Earth, Mars, and then we have the Jovian planets, Jupiter, Saturn, Uranus, and Neptune. But what happened to Pluto? When we were in elementary school, Pluto was a planet. It was demoted to a dwarf planet because we have improved technology, and that resulted in recent discoveries of several distant objects that were similar in size or larger than Pluto. So they had a huge debate over whether to consider the new objects as planets or reclassify all the objects that were similar in size, including Pluto, into a new group of objects. In fact, this particular discussion is still going on. The International Astronomical Union chose then option number 2, to reclassify Pluto as a dwarf planet. The IAU, the International Astronomical Union, adopted a new definition. They said a planet is an object that orbits a star. It's massive enough for gravity to pull its material into an approximately spherical shape. A planet would have cleared the neighborhood around its orbit. Pluto does not meet the last part of this definition and was considered a founding member of a new class of objects, dwarf planets. Since your textbook was published, there have been new developments in whether or not Pluto is actually a planet. As of May of 2018, the IAU recognized Pluto as an important prototype of an even newer class of trans-Neptunian objects. The IAU has a new name. This particular group of objects are called Plutoids. Terrestrial planets. Terrestrial, terra firma, means the earth, land. It's composed of rocks. It's divided into compositional layers. First, on the outside, there's the crust, which are the lighter elements like silicon and oxygen. Then, under that is the mantle. And in the center are the heavier elements. For example, iron, nickel. that are found in the metallic meteorites. What patterns must the Earth-Sun relationship be able to explain? Why is it hotter at the equator and colder at the poles? Why is it colder in winter than in summer? We're talking January and July here because we're in the northern hemisphere. Why is it summer in Australia when it's winter in the United States? Most people think it's because the Earth is closer to the sun in the summer and farther away in the winter. But that is not true. Earth is actually closer to the sun in the winter in the northern hemisphere and farther away in the summer. In the southern hemisphere, below the equator, it's the opposite. The distance from the sun does not contribute to the temperature differences between winter and summer. Well then, why is it colder in the winter and warmer in the summer? The seasonal temperature contrasts are due to the tilt of the Earth's axis and the angle of the sun's rays. The tilt is 23.5 degrees. And there you see, the Earth is tilted on its axis 23.5 degrees relative to the vertical. The tropics of Cancer and Capricorn are 23.5 degrees of latitude north and south of the equator, which is the center line right here. Tropic of Cancer, Tropic of Capricorn down in the southern hemisphere. The amount of solar insolation reaching the Earth's surface depends on the angle the sun's rays hit the Earth. In other words, the steeper the angle, the more atmosphere the sun's rays have to travel through. More heat is delivered by insolation where the sun is directly overhead. Of course, because it has less atmosphere to travel through. The total insolation is least at the poles and greatest at the equator. The solar energy is diluted over a larger area when the sunlight strikes at a low angle, and it has more atmosphere to travel through. There is a layer of the atmosphere that actually absorbs heat and UV rays from the sun. Otherwise, we would be quite warm and crispy. The sun is directly overhead at different places like the tropics and the equator during different seasons. During summer in the northern hemisphere, the sun is directly overhead at the Tropic of Cancer. During winter in the northern hemisphere, the sun is directly overhead at the Tropic of Capricorn in the southern hemisphere. It's directly overhead in the summer. During the spring and fall, the sun is directly overhead at the equator. Note that Earth's axis is always tilted in the same direction, causing the distribution of solar radiation to change with the seasons. Why does the day length change? The hours of daylight? Well, with latitude, the higher latitudes, closer to the poles, they have more daylight than lower latitudes in the summer, and they have less daylight in the winter. With time of year, all locations have more daylight in the summer and less in winter, northern or southern hemisphere. The high latitudes in the northern hemisphere experience nearly continuous daylight in the summer. I've been in Alaska above the Arctic Circle and experienced a 23-hour day and a 1-hour night. It was very strange. Mars has more asymmetrical orbit of the sun than Earth does. Mars is 20% closer to the sun during its winter than during its summer. How would Earth's climate be affected if Earth had a similarly eccentric orbit, being 20% closer to the sun during winter months in the northern hemisphere? The unique composition of Earth. Earth's interior can be divided into three major compositional layers: the crust, the mantle, the core. Well, the crust is the lighter elements, like we said before, for example, silicon and oxygen. The mantle, composed of rocks, make up three key elements: oxygen, silicon, and magnesium is added. The core, which is iron and nickel, is solid in some areas and partially melted on the outer core. It's the source of Earth's magnetic field. Scientists actually recognize two layers with different properties near the surface: the lithosphere, which is the rigid outer layer composed of crust and upper mantle, and the asthenosphere, plastic, slowly flowing layer in the uppermost part of the mantle. The lithosphere is divided into large slabs known as tectonic plates. The plates move over the Earth's surface to produce earthquakes, volcanoes, mountain belts, and various features on the seafloor. The trenches. The geothermal gradient. There's a gradient, and geothermal would be the temperature of the Earth. Geo meaning Earth, thermal meaning heat, and the gradient would be the changes. So there's the Earth's temperature increases. With that, the average temperature rise is 25 degrees Celsius per kilometer. Heat generated, and all terrestrial planets cooled following the formation, and only large planets will still retain the heat. The radioactive decay of elements in Earth's interior. Earth shares many features with other planets, but what makes it special? It's got liquid water, it has gravity and a protective atmosphere, it has life-sustaining gases, and a strong magnetic field. Without any one of those, we would not exist here on this planet. Liquid water is essential for life on Earth, and it's maintained by appropriate temperature range between 0 to 100 degrees Celsius. Venus is too close to the sun. The original water there evaporated into the atmosphere. Water vapor molecules, or H2O, hydrogen, are split by ultraviolet radiation, and hydrogen lost to space. On Mars, it's too cold today to have liquid water, but there is some frozen. Earth's size is actually sufficient to produce enough gravity to hold a thick atmosphere of gases in place. The atmosphere protects us from incoming asteroids and comets and harmful solar radiation, X-rays and UV. Earth's biosphere has altered the composition of the atmosphere to add oxygen and extract toxic carbon dioxide. The atmosphere composition affects the temperature. The higher carbon dioxide content on Venus produces temperatures of up to 464 degrees Celsius. That's very different than Earth. The composition of Earth's atmosphere is just right to absorb enough heat and to keep the average temperature of 15 degrees Celsius. Unless, of course, climate change changes that. The greenhouse effect, which, believe it or not, we do need. The greenhouse effect is with water vapor, carbon dioxide, and they absorb the heat. And without the greenhouse effect, the temperatures would be minus 18 degrees Celsius. That's pretty cold. Earth's magnetic field protects Earth from harmful solar wind that would strip away the atmosphere. The magnetic field due to molten rocks in the outer core and relatively rapid planetary rotation. Smaller planets or slowly rotating planets have lost heat and have weak magnetic fields. That's why Earth is very unique, and they cannot maintain the atmosphere needed for life. This ends Chapter 2.